So this is the example we're gonna be looking at. X cubed plus 4x squared minus 10 equals 0. That's our function, and we are going to be looking for the particular root that's in the interval 1 to 2. As the method suggests, let's quickly get into it. F of 1 is going to be 1 plus 4 minus 10 equals minus 5, and f of 2 equals 2 to the 4, 4 to the 8, plus 2 to the 4, 4, 16, minus 10, so that's equal to 14. So we clearly see a change of sign. That means we can verify that there is in fact a root between 1 and 2. So the way we proceed is to calculate our first guess at the root. The root is going to be, according to our method, it's going to be, we'll call it R, and we'll call it R1. Our first guess at the root is the midpoint of 1 and 2. And the way we calculate it, remember, this is the formula we said, A plus B minus A over 2. So A is 1 plus, I know you can guess the midpoint of 1, the point between 1 and 2 is in fact 1.5, but let's see if the method actually gives us, and you'll see it does. 2 minus 1 over 2, so it's equal to 1.5. So our R1, our first guess at the root, is 1.5. Now, what is f of 1.5? Let's check it. 2.375. Just trust that it's correct. So that's our value of the root. 2.375 is clearly not 0, so that means it's not our root. Now, it means if that's f of 1.5, the midpoint, remember our new intervals, there's two intervals now, 1 to 1.5, or the root is 1.5 to 2. It's in one of these two. So since f of 1.5 is 2.375, and the negative sign is f of 1, that means our this interval, the root is between these two values, clearly, because f of 2 is positive. So that means that what we'll now do is look at the midpoint of 1 and 1.5. And so therefore R2 is in fact going to be 1 plus 0.5 divided by 2, so it's equal to 1.25. So that's our new, that's our R2, our second attempt at the root. And again, we will do the same thing, which is we'll calculate f of 1.25. F of 1.25 is going to be minus 1.79687. We are assuming a decimal accuracy of about, for now, let's say about 5 digits. But that actually works out to be exact in this case. There's no infinite decimals. That's the exact value. So 1.25 is minus 1.79687. Now, when you're doing any calculations, as long as your calculator or the computer doesn't give you infinite decimals, which it won't, it's always going to be finite stuff. But what I'm saying is, as long as it's a finite number of decimal points, please use all the decimal points possible. Get into the habit of doing that, but in reality, in practicality, of course, there will always be 5 decimal points of accuracy, or 6 or 7 or whatever. Usually questions define those. But anyway, let's so here in this case, this is the exact value, minus 1.79687. Now, interestingly, that's negative. Remember, it's our new interval now. There are two intervals to look at, which is 1 to 1.25 and 1.25 to 1.5. Now clearly f of 1, remember, don't keep it in mind, here it is, it's minus 5. Now if it's negative and we take the product of f1 and f1.25, that's going to give us a positive value, which means according to our algorithm, that is not in fact where the root now is. So the root is here. It means it's between 1.25 and 1.5. So we'll take the midpoint of that, and in this way we will continue. If you continue this way about 13 iterations down the road, you'll find that the value turns out to be, in other words, the 13th iteration. So R13 in other words, R13. So dot dot dot. So as we go further, we'll get a value of minus 0.00194. So that would be, sorry, that's not the root, that's f of R13. F of R13 will turn out to be this. Now remember, what's our objective? Our objective is, ideally, we want f of Rn to be 0. But in this case, it's minus 0.00194. Negative, it's not the negative sign. It has no relevance here. It's not important. It's the size of the value. The smaller this value is, the closer it is to the answer. Now, here's where the tolerance part becomes important. Now, you have to decide when are you going to stop searching. Practically, getting to 0 might not be something that may happen. So, one must decide on a tolerance. Otherwise, you could be searching forever. So, in order to do that, you may say, okay, I'm going to stop when my tolerance is less than 0.00001, which means you will keep searching, so you might end up going to R50 or 40 or whatever, and when this tolerance is achieved, when f of Rn, whatever that might be, or Rk is less than this, less than your tolerance, you'll stop searching and you'll be happy with that root. But it's not going to be the exact root, it's going to be the approximate root. Now R13, because I already know what it is, I've calculated it, is 1.365 in fact, and 112305 in fact. Okay, so you could, let me just give you that for completion in case you're looking for it. So R13 here we are assuming is 1.365112305. Now, of course, the bisection method and all of can easily be implemented of all things on Excel, in fact, and I urge you to try, in fact, to do that. I'll show you an example in another video done by another colleague because they've done a good job, and I'm just going to refer you to that video, and I'll put it in the playlist. Thank you very much for your attention.